Okay, this is the spring 25 exam. Here we start. We want to know the electric field vectors at point A. I'm going to start just by drawing those vectors. E1 is going to be in that direction, and then E2 will be in that direction. If these are my X and Y axes, then this angle is going to be the inverse tan of opposite over adjacent. That's 4 over 3. Let's see, that's 53 degrees. So I have that angle is 53 degrees. Now I want to calculate what E1 is. E1 is going to be KQ over R squared. That's 9 times 10 to the ninth. Q there is 25 times 10 to the minus 9 divided by the distance. That's going to be the distance from here to here. This is a 3, 4, 5, or you can say the square root of 3 squared plus 4 squared is equal to 5. So that's 5 meters squared. Let's get some cancellations there, and there. And I'm left with 9 newtons per coulomb. E2 I can solve similarly. It's going to be 9 times 10 to the ninth. That's K. Q is 16 times 10 to the minus 9 divided by the distance, which is 4 meters squared. That cancels, that cancels. I'm now left with 9 newtons per coulomb. So those are my my two electric field vectors. They're equal and but in different directions. So now I need to determine what are the X and Y components. So in our steps, this would be step 1, this would be step 2. Now step 3 is to determine what is E1X and E1Y. E1X is going to be 9 times cosine of 53, and E1Y is 9 sine of 53. This is 5.4, this is 4.5. Each of those are newtons per coulomb. And then E2 is all in the Y direction. E2Y is going to be equal to just 9 newtons per coulomb. Now actually, we'll draw these on their particular axes, but this is negative and then this is negative as well. But let's redraw those X and Y components. I like to do that. It helps me to sort of think about them. I'll draw them over here. So I have E1X is in that direction. That is 5.4. E1Y is in this direction. That's 4.5. And then E2Y is in that direction. That's 9. All of those are newtons per coulomb. So now I want to add those individual vectors. So here I get 5.4. There's no other X component to add to it. And then here I get 4.5. I get that by saying 4.5 minus 9 is equal to negative 4.5. And then this becomes the magnitude of that Y component that's in the downward direction. Now that would be step 4. And now for step 5, I want to find the magnitude and direction. My vector is in that direction. That's E. The magnitude of E is equal to the square root of the X and Y component squared. That's 5.4 squared plus 4.5 squared. Notice I don't really worry about the negatives. The negatives would go away anyway if I included them because they're squared. 5.4 squared plus 4.5 squared. I get 7.0. So that's the magnitude, 7.0 newtons per coulomb. Now I also want to know what this angle is. Phi is the inverse tan of the opposite over the adjacent. That's 4.5 over 5.4. I get 40 degrees. So that is 40 degrees below the negative X, or you could say 220 degrees from the positive X. That would be this angle. Either one of those answers would be correct. All right, let's look at these others. 5 to 6 field lines for this configuration. Now, they're going to originate from the positive like that and go to the negative. And then I'm going to have twice as many. So let's see, so I'll do I'm going to do 3 from that one, and then I'm going to have 3 additional ones come in like this. It's important that you get the direction correct, going from the positive to the negative, the overall shape correct, because remember that the overall shape defines the force. So like, for example, if I have a positive particle here, it feels a force that is in that direction and a force that is in that direction, and the net force is along those field lines. Okay, so the overall shape is important. Get rid of that red. And then the direction. Now I also want you to draw 4 to 5 equal potential lines. I'll draw those in a different color. I'll just do this red. Uh, as they come to a field line, they should meet perpendicular. So this is going to sort of like that. Here it's going to be more curved. Equal potential lines are more curved around bigger charges. At each point, they're perpendicular. All right. Yeah, that's a good map for that dipole with a +3 and a -6. All right, electron moves from point A to point B in this figure. The distance is delta x is equal to 0.2 meters. Let's go back to blue. The red is just so harsh. What is the speed of the electron? So remember, our change in potential energy, or rather, is equal to Q times delta V. That goes back to really our definition of potential. That is that potential is energy over charge. And our change in potential energy, or in this case, our change in kinetic energy, I'll write it as change in kinetic energy because whatever change in potential energy I have, I also have, that change in kinetic energy, is equal to Q times delta V, and that's equal to 1/2 m the speed squared. So if I want to know the speed for part A, I say that the speed is equal to 2Q delta V. What's that? Divided by m, square root of that. I think I did that right. Let's see. 2Q divided, yeah, that's right. 2Q delta V. So that's going to be the square root of 2. Q is going to be, it's an electron, so it's 1.6 times 10 to the minus 19. I'm just asking for the speed. I'm going to leave off that any negative signs. Here I'm going from point A to point B. That's 2 minus -4. So 6 volts. I have a change in potential of 6 volts as I'm moving in this direction. And then divided by the mass of an electron is 1.67 times 10 to the minus 27 kilograms. That's in volts. This is in coulombs. And then that'll give me my speed. So my speed here is equal to, pause this while I calculate it. Here I get 34,000 meters per second. So as this electron moves across a 20 centimeter delta V of 6 volts, it accelerates to 34,000 meters per second. And then in addition, I can calculate the electric, I'm looking for the electric field. So for part B, I'm looking for the electric field. Remember that the electric field, let's go back and we'll look at our equation sheet. So our So I'm looking right here. Our electric field is related to our potential and our delta x, and that way delta V is equal to negative EX delta x. I'm not concerned so much about the direction here. I'm really just looking for the magnitude of that electric field. In fact, I know the direction of the electric field, so I'm just going to leave off that negative sign. So E is equal to delta V over delta x. My delta V, I already know, is 6 volts. My delta x is 0.2 meters. That's equal to 30 newtons per coulomb or volts per meter. So that's our electric field, and that's our speed. This was our electric field here, and that's our direction. By the way, so each of these parts right here would count as a separate question. Oh, I didn't do part E there. I'm sorry. Calculate the potential. So for part E, to calculate the potential at that point, I would say V is equal to KQ1 over R1 plus KQ2 over R2. So that's going to be K times negative 25, 9 times 10 to the ninth, negative 25 times 10 to the negative 9 divided by 5 plus 9 times 10 to the ninth. Q2 was it 16? 10 to the minus 9 divided by 4 meters. I do get some cancellations. These all cancel. This 4 goes into 16 4 times, and this 5 goes into 25 5 times. So I get negative 45 plus 36. That's negative, what, 9 volts. So my potential at point A has a negative potential of negative 9 volts. Okay? All right, so each of those points, each of those parts will count as a separate question. All right, let's look at these multiple choice. Here I have this configuration of charges. I'm just going to draw a force. It doesn't really matter which one I draw first. I'll draw that one first. And then I like to write my Coulomb's law, KQQ over R squared. And as I go from this charge to this charge, recognize that I double the charge and I double the distance. So I get, for the force, a factor of 2 divided by 4, or 1/2. So I'm going to get a force due to that bigger charge, which is further away, that's half the magnitude of the other charge. So as these vectors add up, that means that D is the right answer there. Two electrons are separated by this distance. What is the force? So remember, F is equal to KQQ over R squared. That's 9 times 10 to the ninth times 1.6 times 10 to the minus 19. 1.6 times 10 to the minus 19 divided by 7 times 10 to the minus 12. That has to be squared. And if I do that, I find that the answer is 4.7 times 10 to the minus 6 newtons. Just be really careful with how you put in these in your calculator, that you're using the proper order of operations. I like to use, for the scientific notation, 9E9, and then all that gets sort of, it's like I'm putting it in parentheses here. Now be careful though, because I've seen some students that actually will use 9e to the ninth, and this is different. This is an exponential, and it's not. It has to do with the natural log. It's not what you want to. It's not what you want. That there are two different occurrences. That usually on your calculator, this is listed as EE. Not all calculators have it, but most TIs do. This figure shows two cubes that are experiencing a repulsive force, 1 and 2, and then cube 3 is positively charged. So cube 3 is positively charged, and then cube 1 and 2 are either both positive or both negative because they experience a repulsive force. So let's imagine if this is positive, then that would be okay. If this is positive, well, that doesn't work, right? Because if those are positive, it doesn't work. Or if they're both negative, it doesn't work. And then if this is positive, well, that doesn't work, but it does work if these are negative. Okay, so these scenarios, the scenarios that can occur will be A, if 1 and 2 are positive, or C, if 1 and 2 are negative. B cannot occur ever. So the answer is D, either A or C. All right, what is the direction of the net force on this 3 microcoulomb charge? Oh, okay, so this is relatively easy. I don't have to do any calculations from this because these two charges are the same. So I know then that these forces are the same, which means that I know this makes up an equilateral right triangle. That is, if I have a force there and a force there that are equal, then I know that that angle right there, which is this angle, is equal to 45 degrees because this is an equilateral right triangle. And if that angle is 45 degrees, well, let's see. It would be B is the right answer. 45 degrees below the positive x-axis. 2-point charges are 4 centimeters apart, experience force F. I move them to 2 centimeters. That means if I'm going from 4 centimeters to 2 centimeters, that I'm taking 1/2 of that. 1/2 squared is a quarter. That means I have 4 times the force. Q2 has a magnitude of 6 coulombs. It's actually -6. And I want to know the sign of magnitude of Q1. Well, Q1 is negative, so those all go away. And then I also see that there are 1, 2, 3 field lines, but there's only one field line here. That means that each field line corresponds to a magnitude of charge of 6 coulombs, which gives that -18 coulombs. By the way, this would also be 18, but it would be plus 18. That's how those charges lay out. At what point is the electric field equal to 0? Well, let's just start. We'll draw the electric fields here. I get an electric field in that direction, an electric field in that direction, not 0. Here, I get an electric field in that direction, and in that direction, also not 0. So it's neither D nor E. They can never be 0. But let's look at these different ones. So B, or let's go with C first. No, let's go with B. Let's go with A. We'll go with A first. So A has an electric field due to the big 9 coulomb charge that's in that direction, and due to the Q, which is a smaller charge and it's farther away, it's going to be in that direction. So those cannot be 0. B, I have an electric field due to the plus Q in that direction and due to the 9Q. The distance from here to here is equal from the distance to there. So that's going to be an electric field that is 9 times that charge. So that cannot be 0. So looks like the answer has to be C. Let's see. So the electric field due to the plus Q is in that direction. Remember, electric field is kq over r squared. Notice this distance is 1/3 the distance. 1, 2, 3. 1/3 the distance to the 9q charge. So if I have 1/3 that distance, then that means I have 9 times the electric field. Or rather, maybe think about it this way, that this is 3 times the distance. So I have 1/9 the electric field that I had there. But I have 9 times the charge, so it cancels out and it gives me 2 electric fields that are equal and opposite. So what was that? C? C is the right answer for 7. All right, charged particle moves in an electric field and follows a path shown here. No forces other than the electric forces that act on the particle. What is the sign of the particle? So, if I have a positive particle in an electric field, it's going to feel a force in that direction. If I have a negative particle, it feels a force in that direction. So if it was positive, it would be following a path that looked like that. If it were a negative particle, it would follow a path that looked like that. It's not doing either of those. That means C is the right answer. It's neutrally charged. I measure an electric field. What if I have the distance? What is the electric field? So electric field is kq over r squared. If I have that distance, that's half squared, which is 1/4. I get 4 times the electric field. I'm moving closer to the charge, so I get a bigger electric field. Well, what is the magnitude of the electric field here? Well, let's just calculate it. This is an easier problem from what we did, or a similar problem to what we did in the free response. So E1 is equal to K. Okay, let's just write out the numbers. 9 times 10 to the 9th. 9 times 10 to the minus 9 divided by 3 squared. Cancels, cancels, cancel, cancel. I get 9 newtons per coulomb. E2 is 9 times 10 to the 9th. 16 times 10 to the minus 9 divided by that distance, which is 4 squared. 9. Oh, so it's similar to what we had before. So have 9 newtons per coulomb in that direction and 9 newtons per coulomb in that direction. To find the magnitude, I do the square root of 9 plus the square root of 9. I think that's 13, right? Yeah, 13 newtons per coulomb. 2 charged particles are arranged as shown. They have different magnitudes of the charges, 2 and 4 coulombs. In what region is the electric field equal to 0? So let's see, if I'm over here, I get an electric field that is in that direction towards the -4 coulomb, and some smaller electric field due to the plus 2 coulomb because it's a smaller charge and I'm further away from it. If I'm here, they're both in the same direction. So no matter what the magnitude of the electric fields are, they're always going to add up to something non-zero. But over here, I get an electric field due to the minus 4 coulomb in that direction, and an electric field due to the plus 2 coulomb in that direction. But because the distance to the plus 2 coulomb is smaller than the distance to the minus 4 coulomb, the bigger charge, then that means that there is a place over there where I can get an electric field of 0. And which of these statements is true? Insulators do not easily conduct electricity. That's true. Um, no, a perfect insulator wouldn't conduct electricity at all, but in fact, there is no perfect insulator. Everything eventually conducts electricity, even insulators. Charging by conduction requires the two objects touch. Yeah, that's how we define charging by conduction versus charging by induction where they do not touch. Induction is related to capacitance of an object, not even really a thing. A conductor has electrons, protons, and neutrons. Yes, so I have 1, 2, and 4. When you rub your feet across the carpet, you become electrically charged. Electrons have moved from the carpet to you. You become electrically charged. And we talk about even with the Van de Graaff generator, like the charges were moving around on your body. But remember that positive charges don't move around very easily, that really only electrons move around easily. So the electrons are moving onto you. This figure shows two spheres. They initially have a charge of -2 and -1, and you have this interaction where they shift those charges around. If I now have +1 coulomb on that charge, on that object, what do I have here? We have a total of -3 coulomb. Because charge is conserved, I still have to have -3 coulomb. That means I have to have -4 on that one. Consider this map of equipotential lines. I have a +3 coulomb charge right here, and I want to know how much energy does it gain when it reaches point C. Well, first recognize that positive particles tend to move uh, from low to, from high to low potential. And I'm going from -10 to -30. So my potential is actually decreasing. So that makes sense. And then I want to know how much energy does it gain. Now remember that V is equal to potential energy over Q, or delta V is delta PE over Q. So delta PE is just equal to Q delta V. If I have a 3 coulomb charge and I have a change in potential of -30 minus -10, that's -20 volts. That's equal to -60 joules, or just the magnitude of 60 joules. The energy that it gains as it speeds up is 60 joules. So actually, see here, it loses 60 joules of potential energy, and so it's going to gain 60 joules of kinetic energy. We talked about that in class. Consider this figure. What is the magnitude of the electric field in that region? So very similar to what we did on the free response here. Remember that E is equal to delta V over delta X. So I can calculate the electric field in that way. Delta V, we've already said, is -20 volts. In fact, I'm just looking for the magnitude, so I'm going to leave that sign off. Delta X is the distance, 6 times 10 to the -6. I get 3.3 times 10 to the 6. That's in newtons per coulomb or volts per meter. So C is the right answer. All right, these three charges all are equidistant, and they're vertices of an equilateral triangle. I want to know what statement best describes the electric potential energy. So these aren't actually calculations of the energy, but they give a relative size of them. Remember, potential energy is KQQ over R. So here I would take the product of the two charges, -8 here, -48 here, +24, and then I can just add those up to give me a relative size of the potential energy, which is going to be a negative value. I don't know what, -56, 52, what, -32, I think. Anyway, the point is that it's negative, that the negative numbers are bigger than the positive numbers. What's the potential at point P here? Well, it's just V is KQ over R, but I can recognize that these two charges, which are equidistant 1 meter, will cancel out, that the potential of this one would be negative and equal to the potential of this one would be positive. And so I really just have to do that 10 nanocoulomb charge. That's going to be 9 times 10 to the ninth Q, which is 10 times 10 to the minus 9, divided by R, which is this distance, which is the square root of 1 squared plus 1 squared, which is 1.4. Those cancel, so it's 90 divided by 1.4. That must be 64. These four charges at the corner of a square. Which pair of these statements describe the electric field and the potential? Well, the potential is easy because I have two negative and two positive, so I know the potential is 0. And then what about the electric field? Let's just draw the vectors. I'll start with this one. It's in that direction. That one is in that direction. This charge, the electric field is in that direction, and that one's in that direction. So those electric fields all add up to equal to 0. So E is equal to 0. And then finally, this potential versus position graph. Remember, this isn't a graph of how it moves through space, but it's how the potential changes. So as I'm at point A and I'm moving towards B, or I don't know if I'm moving towards B rather. I want to know if I release an electron. Electron moves from low to high potential. I like to think of a mountain. Protons will tend to move down the mountain. Electrons do the opposite. They move up the mountain. They move to increasing potential energy from low to high. So if I release an electron, it's actually going to move in that direction. As it moves to increasing potential, it gets to this point, but it has this energy because it's like it's been rolling uphill and it has this energy. And so it overshoots and goes over in this direction until it slows down, and then it's going to oscillate back and forth, oscillate around point B. We talked about that in class. And remember, we can use this as an oscillator or a timing standard, much the way that the cesium atom operates as the standard for the second. It's the same idea that I have this charged particle that's what, trapped in this potential well. This doesn't really look like a well because it looks like a hill. We usually draw a well like this where a particle would go back and forth trapped inside of that well, but it's just because it's a negative charge that the well has been flipped upside down. All right, I think that's all. Yep.